I'm ready, yes.
Okay. So hello everyone,
Okay.
welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Vincenzo Nardozza from University of Bari, Aldo, Moro, Italy. The title of his talk is The Grassmann Algebra, Identities, Derivations, and Differential Identities. Please.
Okay, thank you very much. I wish to thank the organizers for giving me this opportunity as a first thing. And then we have to talk with the Grassmann algebra. So this is the sequence of the talks. And I begin with the formal construction. I recall the formal construction of Grassmann algebras. We start with a field, any field, and a vector space of that field. And we simply consider the tensor algebra of the vector space and the ideal generated by these simple tensors. Then the Grassmann algebra is simply the factor algebra of the tensor algebra with respect to this two-sided ideal. It is denoted with the wedge symbol, or is also called the exterior algebra of the vector space. I will denote it by E of V. The E means exterior. Okay, these constructions, in fact, works in general when starting from a more generally from a module over a commutative ring C. But here we have a vector space of our field, and so we can give another presentation of the Grassmann algebra, because if the field is of characteristic different from 2, and we fix any basis of V, the formal presentation is basis free, is independent from the basis. But if we fix a basis of V, then the Grassmann algebra of the vector space can be presented as the algebra, unitary associative algebra generated by the basis, by elements of the basis, with respect to the relations given E1, E2 plus E2, E1 equals 0 for all E1, E2 in the set of generators. Moreover, if the fixed basis is not just a basis, but we fix a total order on it, then we have a natural basis for the Grassmann algebra constituted by all the standard words on the alphabet in B. So all sequences of E1, E2, En, with the E sub I taken in A, listed in strictly increasing order. The Grassmann algebra inherits the Z grading, or better, the N grading of the tensor algebra, but more important is the Z2 grading inherited by this structure, splitting it into two components of degree 0 and of degree 1. So the even and odd component spanned each one by the vectors of the basis, fixed basis, of length even or odd, respectively. Okay. Grassmann algebras are not a joke for algebraists. It is an important object in mathematics, and it is an important object in science as well, more generally in science, because, for instance, it is involved in several important physics topics, like supersymmetry, but also in mathematics it goes beyond algebra, because it is one of the pillars of a general mathematics invented by Félix Bérézine in the middle 70s, which is called the super analysis, or was intended to lead to super mathematics. Book I recall, Introduction to Superanalysis by Bérézine, is actually after was published after Berezin's death in 1980, but it's meaning a substantial book about this ambitious project. In my limited concern, which is PI theory, Grassmann algebras are considered of most countable dimension. The Grassmann algebra in PI theory is the one corresponding to a vector space V with infinite countable dimension. And when the vector space is of dimension n, we denote it simply by E sub n. Why it is so important? Mainly because of the results, the deep results of Kemer in PI theory, when the field has a characteristic 0. Here I recall just two of the results of Kemer. What I call the first one is what I call the bridging property of the Grassmann algebra, which can be stated as any polynomial identity algebra with polynomial identities is PI equivalent. From the point of view of polynomial identities, is equivalent to a finite dimensional super-graded, Z-graded algebra B through the passages through the so-called Grassmann envelope, which is the sum of tensor products. And this property bridges between arbitrary PI-algebras and finite dimensional superalgebra from the point of view of polynomial identities. And then the Grassmann algebra, for instance, occurs in the classification of so-called T-prime ideals, which are full matrix algebra of over F over the Grassmann algebra, and some subalgebras of the full matrix algebra over the Grassmann algebra. This is a theory similar. T-prime. The notion of T-prime ideals is modeled on the theory of prime ideals. T-prime ideals are just ideals which are two-sided ideals, which are prime in the class of T ideals. But also, this is about the role of the Grassmann algebra of an infinite dimensional countable dimensional vector space V. But also, finite dimensional Grassmann algebras have their relevance too in the PI theory, because, for instance, the Grassmann algebras of even finite dimensional vector space E sub 2n are among the so-called fundamental algebras, and their finite tensor products are fundamental algebras as well. Okay, there are countless works about the Grassmann algebras E sub k, or algebras related to the Grassmann algebras with additional structures, for instance, gradings, involutions, and moreover, over any field of characteristic, even positive characteristic, but characteristic has to be different from 2, because the characteristic equal to really poses some problems in PI theory. There was an attempt, a proposed version of Grassmann algebra by Dolkan, Belov, and Vizhna in 2020, which is a characteristic free, so a unifying version of Grassmann algebra, preserving the main characteristic of the usual one, working for characteristic different from. Okay, so I mentioned the algebras. I think everyone knows this notion, but for completeness, I prefer to recall it. We consider a field F, and in my talk, this field is of characteristic 0 always. By the word algebra, I mean an associative unital F algebra, so an algebra with an identity 1. And we consider the free associative unital algebra generated by a set of countable many indeterminates, whose elements are called non-commutative polynomials. And given an algebra A, we say that a polynomial in the free algebra f of x is a polynomial identity for this algebra if this polynomial vanishes under all possible substitutions of the variables by being replaced by elements, any choice of elements of A. The set of such polynomials is not just a set, but it is an ideal, a two-sided ideal of the free algebra, f of x, and it is invariant under all endomorphisms of the free algebra. It is an ideal which is totally invariant. For this reason, for short, it is called a T-ideal of the Grassmann of the free algebra. And the algebra A itself is called a PI-algebra if this ideal is not the trivial one, is not constituted by zero polynomial. That is, there is a non-zero polynomial in the free algebra vanishing on identically vanishing on the algebra A. Then, as a matter of notation, if one starts with a finite, with a set, generally a set of polynomials in the free algebra, the T-ideal generated by S is the least T-ideal containing the set S. And if it happens that this ideal generated by S coincides with the whole ideal of identities of A, one says that S generates the identities of A. So PI theory of algebras studies PI-algebras and studies the related notions. As an object, as a task for one study, if I is a PI-algebra, the main tasks consist in finding a possibly minimal set S of polynomials generating all the ideal idea of A, and in providing a kind of measure on how big this ideal is. If possible, one tries to describe the algebraic structure of this idea. In all these three tasks, the so-called multilinear polynomial are central. Multilinear polynomial, I recall, are simply elements of the n factorial dimensional vector space spanned by all these three monomials in the algebra f of x. So there are monomials of degree n involving just the indeterminates x1, xn, but in any possible order. This is the relevance of this polynomial in this description, toward this task, is because the multilinear polynomials lying in the ideal of identities of A are a generating set for the polynomial identities of A. Okay, it is not generally a finite set of identities, but it is a set of generators for the T ideal. Moreover, this vector space, factoring out the multilinear polynomial of degree n by those ones which are in the T ideal of A, the identities of A, is not just a vector space, but is an Sn module. And its Sn character, denoted usually by Kn of A, describes the Sn structure of the Pn intersected by polynomial identities of A by complete reducibility. So it simplifies the problem of describe the module structure of the multilinear part of the identities of A. Also, the dimension of these modules provide the so-called codimension sequence of A, which is denoted usually by Cn of A, which provides a kind of measure on how big is the ideal of identities. Okay, these are general facts, I think, all well known. But what about the polynomial identities of the algebra, of the Grassmann algebra? Okay, this is today is a well-known result, but originally one has the an obvious identity of the Grassmann algebra, which is called the Grassmann identity. It is formed by the so-called the triple commutator. When I consider commutator in this talk, I consider all commutators, longer commutators, by default left normed. So it is the commutator of x, y, commutated with the z. And this is an obvious identity of E. In 1962, Latyshev proved that the ideal generated by this single identity is Spectian. That is, if it is an identity for an algebra, then the ideal of the identities of A is finitely based. There is a finite set of identities generating all the polynomial identities of A. Later, 10 years later, Krakowski and Regev, by the codimension theory, codimensions were introduced by Regev in 1970. They proved in this particular way that the ideal of identities of the Grassmann algebra E is in fact generated by the Grassmann identity only through this series of inequalities. Later, years later, Olson and same Regev described the structure of the ideal of the Grassmann algebra. It is a sum, its nth co-character involves a sum of irreducible SN modules constituted by hooks of wide one. So a column and with length with wide width 1 and height 1, each with multiplicity 1. Some years later, Vincenzo gave a new proof of the Krakowski-Regev theorem and studied also the identities of the finite dimensional Grassmann algebras and the characters arising from these algebras. We record that the identities of the finite Grassmann algebra were a finite dimensional vector space of dimension n is I don't know how this blue mark was colored on my book. Okay, is obtained by adding to the original Grassmann identity the product of k two commutators of length 2 for minimal k such that 2k is greater than n. In particular, this proves that even and odd following odd n integer, e sub 2 and e sub of e sub 2n plus 1 are satisfy the same identities. Okay. In all I said so far, there is Grassmann algebra, it's important, but where is non-associativity? Because this is a non-associative algebra seminar, so I wonder why I should talk about Grassmann algebra where non-associative is missing so far. In fact, E is the worst example one can produce in talking about non-associativity. Because, if you take an associative algebra, any associative algebra, there are ways to construct non-associative algebras in two ways, natural two ways. The first one is to both of them by replacing the multiplication in A by a different multiplication. One is change the multiplication in A and consider this Jordan product. One get an algebra A plus, which is a Jordan algebra. And a different way, but in the same spirit, one can change the product in A, multiplication in A, by replacing it by the Lie product, bracket product, using commutators. In this case, produces a Lie algebra. But both these methods do not work with the Grassmann algebra, because both E plus and E minus are Jordan algebras and Lie algebras, of course, but they are at the same time still associative algebra. So E plus is a Jordan and associative algebras, so as E minus is a Lie algebra, but at the same time an associative Lie algebra. So E is resiliently associative from, one can say this way, to say with these words. By the way, the non-associativity does not deals with E directly. It will deal with the differential identities of A. That is, one has to take into account the non-associative algebra, derivation algebra of E. And the differential identities of E are precisely this, in a sense, the kind of polynomial identities arising when we want to take into account the action of a set of derivations of E. Okay, this is not an unusual point of view, because there are several additional structures define new kind of polynomial identities. Every time we have an addition in the structure of an algebra, we get the corresponding notion of polynomial identities. If, for instance, A is a super algebra, Z2-graded algebra, then we talk the notion of super identity arise. More generally, if we have a graded algebra by a group G, there is the notion of G-graded G-identities, graded identities. The same for algebras with involutions and so on. Here, so we are considering a set of derivation acting on an algebra A, and this gives rise to the notion of differential identities. The word differential may be alarming, but no analysis is involved in this notion, because in fact, the notion of derivation in an algebra is of purely algebraic one, is a purely algebraic one. This fact was recognized. Okay, I here recalled for maximum clarity the notion of a derivation. Derivation of an algebra is simply a linear operator of the algebra satisfying the so-called Leibniz rule of derivations. And the set of all derivations of the algebra is a subset, vector subspace of the set of the space of linear and endomorphisms of the algebra, denoted there of A. An easy and always available example is constituted by the so-called inner derivation induced by an element, chosen element of the algebra. Take any element A in the algebra, and then define this map, sending any element Y in A into the Lie product, the commutator Y with A, that is YA minus AY for all Y in A. This is a linear. It satisfies the Leibniz rule and is called the inner derivation induced by A. Okay. In fact, this is not a brand new idea in algebra. The algebraic essence of the notion of derivation was recognized first by Ritz, who was an analyst actually at heart. And he fathered a new branch in algebra then, in 1950, named the differential algebra. Kaplansky appreciated this subject and wrote a book on this. But many years after Ritz's death in 1973, it was Kolchin, who was a former student of Ritz, who wrote who provided a unified exposition of the notion of differential algebra and its applications. More or less in the same years, in some very outstanding works of Karchenko, further explored this topic, Kirchenko also introduced the notion, he precisely introduced the notion of differential identity of prime rings, semi-prime rings, worked on rings, but works also on algebras. Okay, so it is far from the brand new idea in algebra. In modern day, however, there is a more general notions embracing all these identities of algebras with additional structures. Because if we let an op algebra H act on an algebra A, then it arises the notion of H polynomial identities of A. And starting from an intuition of Berele in a paper in '96, then sequence of relevant works by several authors, we have the notion of H polynomial identities, identities of an algebra under an op algebra action. And this notion encompasses all these kind of polynomial identities related to additional structures of an associative algebra. Among them, there are also the differential identities. Okay. So, since we have to talk about the differential identities of the algebra, Grassmann algebra, the first thing to know is which are the derivations of the Grassmann algebra. You have to know the description of E of V. Actually, all I found in literature is a paper of Djokovic in '78, who gave the following descriptions for the derivations of the Grassmann algebra. The Grassmann algebra, the derivations of E of V is a direct sum of two vector subspaces, D sub 0 and D sub 1, where D sub 0 is a Lie sub algebra. In this part, the Lie sub algebra of the full derivation algebra. And this works for any, starting from any superalgebra A, actually. And moreover, the Lie bracket between D0 and D1 is contained in D1. And this also holds for any superalgebra satisfying the anti-symmetric property. What is different from more specific of the Grassmann algebra is that the set of inner derivations of the Grassmann algebra constitutes an abelian D ideal of the full algebra of derivations, which is contained in the D1 vector space D1. And D equality holds, so any element of D1 is an inner derivation if and only if the dimension of V is different from Aleph naught, which is a problem because in a PI theory, it is precisely the dimension of equal Aleph naught, the most important case. I have to remark that here we are considering just ordinary derivations. There are other types of derivations taking into greater account the naturals to greater E, and they have to consider, may be considered, they are the so-called anti, or also known as graded derivations. They were typed by Katsai before the work of Djokovic. And there are the so-called skew derivations described by Bavula in 2009. Okay, but the work of Djokovic stated this. Actually, more can be said. Let us fix the case where the finite, the dimension of V is the cardinality of N. And this describe E as the direct sum of its even and odd component. Then assigning any arbitrary map from the basis E to the odd component of E, there are essentially two basic ways to construct a derivation for E. The first one is to extend this map B using linearity and the Leibniz rule directly. And this defines uniquely a derivation delta on there of E. Denote delta, big delta, capital delta, the set of such derivation. Then there is another way of defining a basic derivation of the Grassmann algebra. Start always again with any set theoretical map from the basis E fixed in E and in V to the odd part A sub 1 of E. But one has to choose a map satisfying this relation. This equality must hold for all E1, E2 chosen in E. In this case, the map A allows us to consider another map. We call it D, defined this way. And this map D, uniquely extends to a derivation D in there of E. Let D, capital D, be the set of such derivations. Then the vector subspace stated in the Djokovic theorem are precisely these two sets we are considering here. D0 is precisely the set of delta, is the side of is this delta set, and D1 is precisely the set of D. Okay, we know that D sub 1, that is the set of this derivation D, second kind of derivations, cannot be all inner derivations. But Vincenzo provided an explicit non-trivial example, which is the following. Define this sequence, this map A, from the basis vector of the vector space, the basis elements of the vector space B, E1, E2, etc., and define this sequence A, sending E1 to 0, E2 to E1, E3 to E1, and so on, and then E4 to E1 plus E1, E2, E3, E5, E1, E2, E1 plus E1, E2, E3, and so on. And this is an element of D that is in D1. But this derivation is not an inner one. Okay. What can be proved is that actually the set of derivations of E is the direct sum of D plus delta, and this is known from what I just said so far. But delta is a Lie algebra of their E, and this also is the same as in the Djokovic theorem, but moreover, D is an abelian Lie ideal, properly containing the set of the inner derivations. Moreover, there is in particular, since it is an abelian Lie ideal, in particular, it is a Lie subalgebra, and actually D is a maximal abelian Lie subalgebra of the derivation algebra of E. In the proof of this theorem, the inner derivations induced by simple vector elements of the F basis of V were crucial, and we will meet them again later. This also, the ideas in the proof of this theorem also allow us to compute explicitly the dimension of the Grassmann, the derived algebra of the Grassmann algebra when the dimension is finite dimensional, and the dimensions of D and of delta are distinguished, are different when n is even or odd, and are exactly the following ones. So this is about the derivations of V. What is an action of by derivation on an algebra E? Okay. We recall briefly this notion. Start with the Lie algebra and an associative algebra. We know that the derivation algebra of A is a Lie subalgebra of the full algebra of linear transformations of A. With respect to the bracket product, is a subalgebra of GL of A, talking about in Lie terms. The only difference, the only care to take is in this talk, and we are going to use adopted exponential notation. So derivations acts on the right of the elements of A, and since this the composition of linear derivations is meant left to right. First A alpha and then beta in this part, and then we first beta and then alpha. However, we say that this Lie algebra acts on A by derivation means that simply, for short, we say A is an L algebra, means that there is an assigned Lie homomorphism from the Lie algebra L to the derivation algebra of A. And in associative terms, this means that it turns A into a right, because we are acting on the right, module for the universal enveloping algebra U of L of the Lie algebra L. Then these are consequences. In fact, the image of this homomorphism inside the linear transformations of A generates an associative subalgebra, which is isomorphic to a factor of the universal enveloping algebra of L, factored out with a suitable kernel K, and also as an L homomorphism, that is an homomorphism preserving the structure of L algebras, is simply an algebra homomorphism commuting with the L action. This means that we get an algebra on which the algebra acts by derivation, which is what is a differential polynomial identity, so a differential polynomial. We have to define a free object of differential polynomials. This construction is also extremely simple and basis free. We start with an infinite set of indeterminates. Consider this vector space, which is the tensor product of the vector space spanned by these indeterminates, tensorized with the universal enveloping algebra of L, of the Lie algebra L. And call with this symbol its tensor algebra. It has a natural structure of L algebra, on which, on this algebra, the Lie algebra L acts in a natural way. And moreover, this object, f of x sub L, is a free object in the class of L algebras. A free object on the set X, this set. Any map, if A is an L algebra, any map defined from X to the algebra A uniquely extends to an L homomorphism. This is basis free, but since we can fix an ordered basis in the algebra L, by the Poincaré-Birkhoff and Witt, we get a canonical word, a canonical basis for the universal enveloping algebra, which we denote by U. And then we make the following identification. Take an element, a free variable. Take an element in this basis, and instead of writing X variable tensor U, this basis element, write directly X sub U, X under the action of the element U, products of derivations. We identify X under 1 unity as X, and these are the ordinary, so-called ordinary letters. The set of such differential letters generates a free associative algebra, which is isomorphic to this free object. So it is simple to consider this construction and to get a free object. Elements of this object are called differential polynomials, and then all definitions came easily. We get a a differential polynomial identity of A if we have a differential polynomial vanishing under all substitutions of the elements of the indeterminates X by elements of A. The set of all such polynomial is a two-sided ideal of the free L algebra, which is invariant under all endomorphisms, a PL ideal. And the notion of TL ideal generated by a set of differential polynomials and the notion of a basis of identities, of differential identities for an L algebra arose very naturally. In this framework, also the multilinear polynomial, differential multilinear polynomial play their role analog to the one ordinary multilinear polynomial play for ordinary algebras. That is the set of differential multilinear polynomial, that is all polynomials which are in the span of these monomials, differential monomials, are denoted by Pn of L sub L to the L, differential under the L action, and the slices of all polynomial of this kind generated by in the ideal of differential identities of A generate the whole TL ideal. Also, this factor space is an SN module, and its character SN character called the differential characters describe the sense and structure of the multilinear space inside the differential ideal of identity by complete reducibility, and the codimension sequence, which is simply the dimension of this vector space, provides a kind of measure on how big is the ideal of differential identities of A. There is a basic warning. Unlike the ordinary case, it may happen that these codimensions, the dimensions of this space may be infinite. This does not occur in ordinary case. There was, starting from 2019, there was a sequence of papers dealing, studying the differential polynomial identities of concrete algebras, which were finite dimensional algebras. I named some of them. The only one dealing with a non-finite dimensional algebra was by Rizzo in 2020, where he studied the differential identities of the Grassmann algebra E under a finite action, a finite set of inner derivations, but inner derivation are part of a Lie ideal, an abelian Lie ideal. Hence, they generate an abelian Lie algebra. More recently, Vincenzo and myself studied the differential identities of the Grassmann algebra under the action of some finite dimensional Lie algebras. In our methodology, method we adopted were different from the one used, for instance, by Rizzo in his work, because we can notice that since the characteristic is zero, as in Rizzo consideration, we may consider differential multilinear polynomials. But since E is also a unital algebra, we can study the identities of E by means of multilinear proper polynomials, not just multilinear. What is a multilinear proper polynomials? It's difficult to explain in full details, but I think it would be enough to describe them in this way. A multilinear polynomial F, differential multilinear polynomial F, is proper, is called proper if it can be written as a linear combination of products C1, C2, Ck, where each of these factors, C, equally C, is a Lie product of elements of XL, or we can say it is a generalized higher commutator Z1, Z2, ZL, where these elements are in XL. but we have to specify that here we are considering scalars as commutators of length 0, and differential letters, really differential letters, non-ordinary letters, are considered commutators of length 1. So in fact, these definitions means that a multilinear polynomial is proper if and only if its ordinary letters occur in commutators only. The other one can go outside commutators. For instance, if the Grassmann identity is a multilinear proper polynomial, in particular, it is a differential multilinear proper polynomial because these are ordinary letters. The differential polynomial f, which can be written, here is written in normal form, but can be written this way, is a multilinear proper polynomial because it is a product of a commutator of length 1 and a commutator of length 2. And all ordinary letters occur in commutators only. Instead, the polynomials g and h in this example are multilinear, differential, but not proper ones. Why to use these proper polynomials? Because, okay, denote gamma n l to the gamma ln this set of polynomials. And the basic properties are the following ones. They form this factor space is an Sn module. His Sn character is denoted by Cn of L. Okay. Its dimensions, called the nth differential proper codimension of L, is this one. And this characteristic of multilinear proper polynomials are related to the multilinear polynomial in a through very easy, very understood connections. These are the properties. The slices, these slices, when considered just multilinear proper polynomials lying inside the ideal of differential identities, they generate the whole ideal as well as the multilinear polynomials, the simple multilinear polynomials. So they are good substitute from the point of generating the identities. The characters, the differential co-character sequence of A is Young derived by the proper one. That is, this is the co-character sequence of A. This is the proper co-character sequence of A, and the link between these two objects is obtained through the Young's rule to form this tensor product of characters, and then inducing in Sn, and we get through the Young's rule, and we get the co-character sequence of A. Also, from this relation, it follows also these relations between the codimension, differential codimension of A and the proper differential codimension of A. By the way, using this methodology and these polynomials, we were able to prove several results about A. At first, we considered that an algebra generated by some derivations I denoted as partial 1, partial n, all chosen in D, not necessarily inner derivations. Then we can say that all these three polynomials, very simple, are identity of for E under the action of this generic L. We don't know which are all the identities because it depends on which are explicitly these derivations fixed. But at least for sure, these are among the differential identities of E. Then we consider, for specific case, each of these derivations is an inner one, derived by, induced by some elements of the basis of the Grassmann algebra, B1, of even basis of the odd component of the Grassmann algebra, B sub 1, basis of E sub 1. Actually, we consider just two extreme cases, opposite cases. This supports, that is, the set of elements of E occurring in each QE form pairwise disjoint subsets. This is the setting of Rizzo's original paper. And we get, again, we recover this result that the ideal of identities of E is generated by this, not three, okay, these are more than three, but this kind of, for E and J, any arbitrary E and J, is generated by these three identities, the least case. In this case, these three are precisely the generating set of the ideal of identities of E. And then the opposite case, in some sense, is when the supports of this QE are not pairwise disjoint, but form a chain. And in this case, the identities of E follow from these polynomials, where these first three writings are the same as before. One has to add this further writing. Then we can describe the codimensions and co-characters of this algebra, of this idea. Then we consider a more difficult case. We consider the algebra of dimension 2m dimensional, which is not abelian. Precisely, we consider any fixed map. If we have a constant map, there are two ways to define a derivations. One, consider the map sending each element E of the basis A in D in E sub E. The two ways we can use this map to define derivations are to define a D derivation in this way, which is simply the inner derivation defined by the element, the basis element E sub I, and the derivation obtained by extending the original maps, the constant map. Okay, so we get two M derivations. M of them are in D, M of M are in delta, and they generate a Lie algebra whose non-trivial products are simply summarized in this line, thus getting a solvable, not abelian, solvable Lie algebra of index 3. And this algebra acts on E and gives rise to the following description of the polynomial, differential polynomial identities. So you see these blue writings are precisely the same identities as before, and come from the fact that a part of these derivations, because it's constituted by inner derivations. But there are these other two relations, two polynomials involving double derivations and a sum, doubly derived letters. To prove this, we have to consider, to describe, to prove this equality, to prove this theorem, one has to describe explicitly a basis of the vector space gam n of L and gam nl of E, which is rather complicated because it is if n is greater than a number of derivations, or n is greater than m, then we have this kind of normal form for the vectors, for the polynomials in the factor space, which are products of commutators, then products of ordinary letters, then products of commutators in delta letters, then a word in delta letters, and then a word in D letters. And this is according to the parity, which is if the number of ordinary letters and the number of delta letters occurring in commutators must match, both even or both odd. In case they are both odd, there should be this mixed commutator linking an ordinary letter and a delta letter in commutator. Okay. So this is the general form, and all this vector I wrote this way in order to make me more understood. A product C of commutators in ordinary letters, then maybe a mixed commutator, then a product of delta commutators of delta letters, then a standard word on delta letters, and a standard word of the letters. This for all four tuples H, K, R as non-negative satisfying this request. But if M is less or equal than N, to those vectors, one has to add further vectors involving no ordinary letter at all of this form, and which is more or less described. I think it would be understandable. Our standard word on delta D letters, doubly derived letters, then a product of commutators in the delta letters, and a standard word on delta letters, and then a standard word on D letters, satisfying these requirements. However, once this has been proved, we proved that the nth differential proper Esenko character of E is this one. This is the sum obtained when this 5 tuple ranges among the 5 multisets of n. That means that there is no order, but this sum has to be n. Sum of these elements has to be n. And satisfying the following requirements: if h is greater than 0, then L is 0 in this value. And h and k have to be congruent modulo 2. And this is apart from this binomial coefficient, is essentially the induced character of a triple commutator between two sign characters and a trivial character. So it's complicated in writing, but it's easy in notion. By the way, by this formula, we computed the proper codimension sequence, which is this sum. This is a binomial coefficient. This is a trinomial coefficient. It's a multinomial coefficient n over h plus s r k plus l, which, and after manipulation of these numbers, we were able to prove that the limit, this limit for n ranges to infinity of the nth root of this of the number CNL of A, this is gamma NL of E. We have to manage CNL of it via the relation I illustrated before. This limit does exist and is precisely 2, which is the same as the so-called ordinary exponent of the Grassmann algebra. Okay, this is not really surprising from my point of view, because when A is a finite dimensional algebra, Gordienko already proved that the exponent, the differential exponent of A does exist and it is an integer. And later Gordienko and Kochetov proved that not only it is exists and is an integer, but it equals the exponent of the algebra A, ordinary exponent of the algebra A, when L is a finite dimensional semi-simple. So I is finite dimensional and L is finite dimensional and semi-simple the algebra. Later, Rizzo in 23 actually proved that if A, it is enough when A is finite dimensional and L is any Lie algebras to have that the exponent of differential exponent and the ordinary exponent of A do coincide. In our case, the difference is the fact that A, our algebra, is not finite dimensional. E is infinite dimensional. But all the same, this happens. Okay, here this talk is based on these two very recent papers. This with Vincenzo, and this was already submitted. This is a short. For at the moment the title yet to be submitted, and here there is a full list of references of the results of the papers I cited. I give the possibility to track down something useful. There are not very many papers. Almost finished. Okay. And in the end, I thank you very much for your attention. I hope you enjoyed the talk, and say you goodbye.
Thank you very much for a nice talk. Other questions? Well, if not, thanks again, and thanks for accepting the invitation, and I wish you all a nice week.
Thank you very much. See you soon.
Yeah.
Thank you very much once again.
Yeah,
Goodbye to everyone.